Hello everyone. I have prepared a diagram for cloud architecture for digital TV. And let's begin. And let me zoom. Here we have the physical layer. This is the layer where all the IoT sensors and devices exist. Think of it as a starting point for data collection in the real world. And these devices are responsible for gathering raw data from various environments. It could be temperature readings, motion detection, or even more complex metrics depending on the use case. And this data doesn't just hang around. It gets encrypted right here to ensure it's secure before moving to the next layer. And it's okay. Moving on to the edge layer, which acts as a sort of intermediary. This layer handles two main tasks. First, we have the IoT gateway. Here you can see, you can think of this as a translator. It manages all the devices and translates their communication protocols into something that the system can understand. It's like taking multiple languages and turning them into one standard format. And we get into edge processing, and this is where local analytics and buffering come into play. Instead of sending everything directly to the cloud, this layer processes the data close to where it's being generated. It filters out unnecessary noise and performs some initial analytics, which saves the time and reduces the workload for the cloud. And uh, to make it all more reliable, we have got edge caching. This provides data redundancy, ensuring that even if there is an interruption, the data is not lost. And okay, next look at the security layer, which spans the entire architecture. Here you can see like that. And its role is to protect the data at every stage. Here we have two key components, authentication and authorization. These two ensure that only verified users and systems can access the network. It's like a bouncer at a club, only letting the right people in. And alongside that, there's a role-based access control, which is a bit more nuanced. It assigns different levels of accessing depending on the who you are or what your role is in the system. For example, an administrator might have full control, but a general user might only be able to view certain data. And this minimizes risks and ensures that sensitive operations are handled only by those authorized. And here, uh, overarching all of this is end-to-end encryption. This guarantees that from the moment data leaves the IoT devices to when it's processed or stored in the cloud, it remains secure and tamper-proof. Even if someone intercepts the data along the way, encryption ensures they can't make sense of it. Okay, and here cloud platform, and first here at the data ingestion layer, we have two main components: the load balancer here and combination of stream processing and message queues. The load balancer is responsible for distributing incoming traffic efficiently across the system. This ensures that no single part of the system gets overwhelmed with data. From here, data flows into stream processing, you can see here, which handles real-time data as it arrives at message queues. like Apache Kafka or RabbitMQ, which manage asynchronous communication. These queues help buffer and organize data to ensure it moves smoothly through the system even when the flow is high or irregular. Okay, and let's look at here. Here data transitions into the data processing layer, and this layer starts with real-time analytics, a critical component for processing data streams and generating immediate insights. Think of this as the layer where raw data starts to become actionable. And uh, from real-time analytics, we see connections to other components. And first, there is rule engines, which applies business logic to the data. And this engine is what automates decision making based on predefined conditions. For example, if a sensor detects an anomaly, the rules engine might trigger an alert or adjust a system parameter. And second, the data is fed into machine learning models. Here you can see, which are predictive systems. These models are trained on historical data and are used to predict future trends or events. Okay, and here we'll talk about data storage layer. Here we have several interconnected components and time series databases you can see, and stage management, and here data lake. Data flows from the processing layer into the storage layer from different purposes. And again, here the time series database specializes in storing historical data, which is critical for trend analysis or training the machine learning models. And here, the state management system tracks the current status of the system, essentially providing a live snapshot of what's happening. And meanwhile, the data lake acts as a raw data repository. It's a place where all data, processed or unprocessed, can be stored for future use. Okay, and here one important connection we see here is between the storage layer and the backup system. This system ensures disaster recovery by regularly backing up critical data. So even if there is a failure somewhere, the system can recover without significant data loss. Okay, and I'm looking. That's okay. That's okay. They are done. And everything is done now. Okay. Let me zoom like that. Okay. Now we'll focus on this section of the architecture, starting with the digital twin services. Here, two key components are working in tandem: simulation engine and 3D visualization. Here you can see. The simulation engine is responsible for running what-if analysis. Think of it as testing ground for scenarios where potential outcomes are simulated based on changes in variables or configurations. This is invaluable for predictive planning and optimization, as it allows you to foresee the results of decisions without impacting the actual system. And connected to the simulation engine is the cache layer here, which ensures performance efficiency. And now, why is this cache important? Because simulations can be computationally expensive and frequently accessed results or data don't need to be recomputed every time. The cache layer steps in to store this information temporarily, speeding up processes and improving responsiveness. And on the other side, we have 3D visualization, which creates interactive visual models of the system. And this component bridges the gap between complex data and human understanding, giving users a clear and interactive view of how the system behaves. The data feeding this visualization often comes directly from simulations or processed information from the storage layer, creating a seamless flow of insights. And okay, uh, now all these services and their results are made accessible through the REST GraphQL API, which serves as the interface between the backend systems and users or external applications. This API plays an important role in ensuring that the insights, simulations, or visualizations are available in a standardized format that can be easily integrated with other tools or platforms. And moving into the application layer, we see three main outputs. At first, there is the web dashboard, which is the primary user interface for monitoring and interacting with the system. And this could include live data visualizations, control options, or reports. And then there are mobile apps and which provide remote access to system. These apps are designed for users who need to stay connected on the go, enabling quick checks or adjustments from anywhere. And finally, there is third-party integration. This component ensures that external systems or tools can connect to the architecture, extending its functionality. For example, a manufacturing system might integrate with ERP software for inventory updates or compliance monitoring. And what ties all these pieces together is the seamless flow of data between the digital twin services and the application layer. And insights generated by simulations and visualizations are not just confined to technical users, they are made accessible to decision makers and operators through user-friendly interfaces and integrations.